Okay, I think we may start. Is it fine? Are you ready?
Yes.
Okay, good. So thanks everyone for joining this talk. This is a very big pleasure for me to introduce Anuj Dawar. Well, I don't think that any special introduction is needed here because Anuj is very well known for a wide audience for his major contributions in computer science and especially his connections with logic. So yeah, it's really a great pleasure to have you on our seminar. Please, welcome.
Okay, thank you very much for the introduction. Thank you very much for the invitation to speak here. This is my second occasion speaking at Moscow PhysTech. Once I was there in person, and now I'm there virtually. I'm going to talk, like it says, about circuit lower bounds assuming symmetry. And specifically, I'm going to talk about some recent work with Gregory Wilsenach, who's a postdoc working with me currently. And we had a paper which we presented at ICALP 2020 last summer on symmetric arithmetic circuits. And I will talk about the results in that paper and some recent follow-up work, which is not yet published as well. Can I just check? The time for this is, I saw the slot was 90 minutes. Is that, when should I?
Yeah, that's right. But we are flexible with it. If you want to speak a little bit more or a little bit less, this is.
That's fine. Okay, thank you very much. So I said symmetric arithmetic circuits. So we'll start with, let's see. An arithmetic circuit is an object which looks a bit like this. What do I mean? So think of it as you can think of it as a model of computation, or you can think of it as a formalism for writing down polynomials in a compact form. Think of this, the circuit, think as a model of computation, think of it as going from top down. So at the inputs, we have variables like x, y, and z. And we have constants like -1 here, or this is a 3. And then we have internal gates where we perform operations of multiplication or addition. I'm allowing no other operations. So every gate, as we call it, in the interior can be seen as computing some polynomial formed by additions and multiplications from the input. And there is a designated output gate over here. And if you work it out on this one, I mean, there's nothing special about this polynomial. I just wrote down a circuit pretty much at random. You get the polynomial minus x squared y minus 9xz squared. Okay, that's what this particular circuit computes. Formally speaking, we have a field K, and an arithmetic circuit over K is given by a directed acyclic graph. Every input, that means every node in the graph which has no incoming edges, is labeled by either a variable from some fixed set x or a constant from the field. All other gates are labeled by the operations addition or multiplication. Then one designated gate is the output, and that computes a certain polynomial. Okay, it's obviously a polynomial in the polynomial ring given by this set of variables x. Now, in the field of algebraic complexity, there is a conjecture of variance, which is known as VP versus VNP. It's an algebraic analog of P versus NP. It's been open almost as long. So here, VP means those polynomials which can be computed. I wrote computes or represents. As I told you, you can think of this as a model of computation, or you can simply think of it as a syntactic representation of a polynomial in a compact form. VP is those polynomials which can be represented, polynomials of polynomial degree in the number of variables, and which can be represented by polynomial-size circuits. VNP, the definition is a little bit technical. There are sort of polynomials which are obtained as projections of polynomials in VP in a certain way. But Valiant conjectured this and said this was in some sense maybe a somewhat easier problem to approach than P versus NP. It's not entirely analogous, and there is no implication either way known. I think it's known that if VP equals VNP, then you get a collapse of the polynomial hierarchy to some finite level, but I don't remember the exact details of that. But the point is that this problem has remained open for 40 years. It was formulated by Valiant in 1979, and it remains as elusive as the P versus NP problem. Okay. Now, the polynomials we're usually interested in, often, I should say, are entries of a matrix. What do I mean by this? That means that the set of variables over which we form the polynomials, you can think of as labeled by indices I and j, where I ranges from 1 through m and j ranges from 1 through n, say. So you think of this as an m by n matrix of variables. We're especially interested in this case where m and n are the same, so we have a square matrix. I'll take you through 3 examples, which will be the examples that will appear further on in my talk. Consider this. This is a polynomial which is simply the sum of the diagonal entries on the matrix. This is, of course, the trace of x. Okay. This is a somewhat trivial case. A more interesting polynomial is what we call the determinant. You're all familiar with the determinant of a matrix, written as a polynomial in the variables xij. It is the sum over all permutations of n, right? So now we have this, we're looking at the case where m equals n. So I and j range from 1 through n. So you take the sum over all permutations of the signed product of xi sigma I. So you multiply for all I xi with sigma I, and you multiply that by the sign, which is 1 if the permutation sigma is even, and -1 if it is odd. A related polynomial is the permanent of the matrix X, which is the same expression except I drop the sign term. Okay, so it is simply the sum over all permutations of this product. We call this the permanent of X. Now, the determinant as a polynomial is in VP. You wouldn't know it from the expression I wrote because that expression was not a polynomial size circuit. But you take a routine algorithm for computing the determinant, like a version of Gaussian elimination, and you can implement it as a circuit. It's not direct implementation because we don't have division in our circuit, for example. We don't have the division operation, which would be necessary to do Gaussian elimination directly. But and so, our circuit really computes a symbolic determinant, right? But you can show that this can be done. It can be implemented, and there is a circuit which shows that with a polynomial number of addition and multiplication operations, you can express the symbolic determinant. The permanent, on the other hand, Valiant showed is complete for the class VNP. In other words, if you could do this, if you could do the permanent with polynomial size circuits, then VP equals VNP, and it would dramatically change our view of the world. So Valiant's conjecture is that you cannot do this, that the permanent cannot be expressed by circuits of polynomial size. So Valiant conjectured that VP is different from VNP. I've not given you the definition of VNP. I treat the conjecture as simply saying this, that you cannot express the permanent with circuits of polynomial size. Now, the conjecture remains open. There has been some progress. People have established lower bounds for arithmetic circuits for restricted models. So you put restrictions on the kinds of circuits you consider. One early result is, say that a circuit specifically over the real field is monotone if all the constants you use are non-negative. And back in 1982 already, Jerem and Snur showed that there is no monotone family of circuits of sub-exponential size for computing the permanent. Another significant restriction is obtained if you bound the depth of the circuit. The depth means the longest path from input to output. And it's known, for instance, that there is no sub-exponential size family of depth 3 circuits for computing the permanent over any finite field. Now, both these results have been generalized to other fields. I give you the original form. But one thing to note about these is that they prove this lower bound not just for the permanent, but it turns out the lower bound also applies for the determinant. And so in some sense, it doesn't separate the two, right? These lower bounds are really showing that in some sense, the model is very weak, right? Once you consider only monotone circuits or bounded depth circuits, it seems it's the model that's weak because you can't even do the determinant, which we know you can do in polynomial-size circuits in general. So in our work, we consider another restriction. This restriction was inspired by work we did in logic, but in some sense, there'll be very little logic in what I tell you. We consider a restriction on circuits, which we call symmetric circuits. And with respect to such restrictions, we prove, I'll show you both upper and lower bounds for computing the determinant and the permanent, which I think are quite interesting. And in particular, they do demonstrate some fundamental differences between the determinant and the permanent. So what do I mean by symmetric circuits? So suppose we have a polynomial p over the variables x in the field k, and we have a circuit computing this polynomial. Consider the group of permutations of the variables, right? This is just a full symmetric group, sim x. And let gamma be a group acting on x. So in particular, it could be just a subgroup of sim x, but in some cases, it's more convenient to think of it as a different permutation group with an action on x, as we will see. We say that the polynomial is gamma symmetric if whenever you apply any permutation in gamma to the variables of p, right? So gamma is acting on the variables in x, that induces an action on polynomials. And we say the polynomial is gamma symmetric if applying this permutation in gamma to p, we get back the same polynomial. We say a circuit is gamma symmetric if you apply a permutation from gamma to the inputs of x, you can extend the permutation to all the gates of the circuit to get back the same circuit. Okay, so in other words, you can extend the permutation and you get an automorphism of the circuit. That's what we call a gamma symmetric circuit. So let's look at some examples. If we have a set of variables, there is a class of polynomials we consider the elementary symmetric polynomials. So in general, people use the term symmetric polynomial to mean any polynomial on the set of variables, which is what I would call sim-x symmetric. It's invariant under all permutations of the variables. Among these, there is a basis of elementary symmetric polynomials. I will just take one particular example. Just take the simple example, which is you have a set of variables. So my set of variables x is, now this is not a matrix. This is just xi in the range I from 1 to n, right? And my polynomial is simply the product of all the variables. Then clearly this polynomial is symmetric under arbitrary permutations of the variables. You simply get the same product. And I can compute it with this circuit, which is symmetric in the sense any permutation of the input variables gives me the same circuit. Consider this alternative circuit for computing the same polynomial, which is sort of a binary tree where I multiply first x1 and x2, separately x3 and x4, and so on. If n is a power of 2, this will be a complete binary tree, right? xn minus 1 to xn. And then I multiply the next things pairwise and so on until I get the output. So the height of this is something like log n. But this has the fact that every gate has exactly 2 inputs. Now this still computes this symmetric polynomial, but obviously the circuit is not symmetric in the sense that if I apply the permutation, for instance, which exchanges x1 and x3 and leaves all other variables fixed, this does not give me an automorphism of the circuit because there is a gate which connects x1 and x2, but there isn't a gate which connects x2 and x3. Okay. This circuit has some symmetries. So this is gamma symmetric for some subgroup gamma of sim n. And you can work out what group it is. I mean, it's not so easy to describe. Obviously, it includes all the pairwise swaps of x 2i, sorry, xi 2i minus 1 with x 2i. And then, of course, you can perform further swaps here and so on. I won't spell it out. But the point is, this circuit is gamma symmetric for a proper subgroup of sim n. Okay. And one conclusion is fan-in matters. So it's common in the field of arithmetic complexity to say that you can always replace these large gates with fan-in 2 with only a polynomial increase in the size of the circuit and maybe a log n factor increase in the depth. But we can't do that while preserving symmetry. So it's important that our gates, our multiplication and addition gates, take arbitrary number of inputs. Okay. Because we're interested in as high symmetries as we can get. Okay. So I hope it's clear what I mean by symmetric circuits. And I should probably have said at the beginning, but let me say this now. Please do feel free to interrupt me at any point if something is not clear and you have questions, because we have time, so we can. I'm happy to take things slowly. Okay, let's see. So let me consider some. So I gave you an example now where the full of a polynomial and a circuit which was invariant under the full symmetry group on the set of variables. Now I'm going to consider some restricted symmetries. For instance, suppose our set of variables is xij with I and j ranging from 1 through n. So in some sense, we're looking at our input as a matrix. If we take the full symmetry groups on X, this is actually not a very interesting thing from the point of view of a matrix. What polynomials are invariant under all permutations of the entries of the matrix? I mean, you're essentially forgetting everything about the matrix structure. So not so interesting. But consider, for example, our polynomials, which are the trace, the determinant, and the permanent. They are in particular all invariant under the action of sim n given by, when you apply a permutation to xij, you take it to x pi I, x pi j, right? This is what I call simultaneous row and column permutations. This means you have rows 1 through n and columns 1 through n, and I apply the same permutation pi to the rows and the same permutation pi to the columns. This does not change the trace of the matrix. It does not change the determinant, and it does not change the permanent. Okay. So all of these are what I would call sim n symmetric polynomials. In particular, this particular action I call square symmetric. By that I mean the action of sim n on the set xij given by this action. If you look at the permanent, this actually has certain further symmetries. I can actually apply a permutation to the rows and a completely different permutation to the columns, and I still don't change the permanent, right? Because this is the sum over all sigma of the product xi sigma I. So, I mean, just composing sigma with another permutation all through doesn't change the permanent. So basically, the permanent is invariant under the action of sim n cross sim n, where given a pair of permutations, I apply sigma to the rows and pi to the columns. This doesn't change the permanent. But note, right, so I call this the matrix symmetric action. Note, the trace and the determinant are not matrix symmetric. In the case of the trace, I mean, the trace is simply the sum of the diagonal, and if you apply one permutation to the rows and a different permutation to the columns, you change the diagonal. In the case of the determinant, if you apply a permutation to the rows and a permutation of opposite sign to the columns, you change the sign of the determinant. Okay, so the determinant is not invariant under arbitrary row and column permutations. What is the symmetry group of the determinant? Well, it's fairly rich. You can apply any pair of permutations, sigma to the rows and pi to the columns, as long as they have the same sign. And you can also transpose the matrix. Okay, so this I call the symmetry group of the determinant. I call it D. So the determinant is D-symmetric for this group, D with its natural action on the matrix. In particular, I'll be interested in a subgroup of D, which is the pair of, I'll forget about the transpose, but consider those pairs of permutations where both of them are even, and I call that all 10 by all 10. Or I call this the even matrix symmetric action. So apply an even permutation to the rows and an even permutation to the columns, and it obviously doesn't change the determinant. Okay, so with that, I've told you what I mean by symmetric circuits, symmetric polynomials. And if you look at this definition of the determinant, you can write this out as a circuit. It's a circuit of simply depth 2 because it's a big sum of products of, and each of these products is of some n input variables, right? So it's a bounded depth circuit, but the size of the circuit is of course n factorial because the sum is over n factorial terms, where each product is over n variables. So this gives you a rather large circuit, but it is a symmetric circuit under this full group of symmetries. Okay. We know we have small circuits for the determinant, for instance, Gaussian elimination, but those circuits are not symmetric. Gaussian elimination doesn't give you a symmetric circuit because the Gaussian elimination algorithm really proceeds by choosing a pivot, right? You choose a row with respect to which you do it. I mean, it doesn't matter which pivot you choose. Ultimately, the algorithm converges to the same answer. But the choice of a pivot is a symmetry breaking operation. To do it symmetrically, you could do them all in parallel, but this leads to exponential size circuits, and we can prove that. Okay. So Gaussian elimination doesn't give us symmetric circuits. There is something else we can do. There is Leverrier's method, shows how to compute the determinant, at least for fields of characteristic 0, from the traces of the powers of the matrix. I mean, I won't, this is a standard method. I'm not going to give you it, but basically it allows you to in fact derive all the coefficients of the characteristic polynomial by a simple recurrence from these values alone. Now clearly, okay, we can compute the powers of X. Matrix multiplication can be implemented as a square symmetric operation, right? And once you have these powers, computing the trace is just looking down the diagonal. It's taking the sum. It's a square symmetric operation. So you can implement this and you get polynomial size sim and symmetric circuit for the determinant, right? What I call square symmetric. So symmetric under simultaneous permutations of rows and columns, where you apply the same permutation to the rows and the columns. What about the permanent? You look at the defining expression for the permanent, and again, just like with the determinant, you get a symmetric circuit, matrix symmetric, of size n factorial. We can do better. The best known circuits for computing the permanent are given by this thing, which is called Reiser's formula. This is, instead of n factorial, your sum is now over subsets of n, so it's 2 to the n. This sum is now of size 2 to the n. So it's better than n factorial. I mean, this is simply the best known circuit without any considerations of symmetry. This is the smallest known circuit for computing the permanent. And it turns out it is, in fact, symmetric in the sense that I define matrix symmetric. If you permute arbitrarily the rows and separately the columns, you get the same expression. So Reiser's formula is, in fact, a symmetric circuit. So, and the size is roughly, as I said, n squared times 2 to the n or so. Okay. With that, I can now at least tell you what the results are. Where I'm, half an hour into the talk, I can state my results, and then I'll give you some ideas of the proof methods that go into these results. So we look at both the determinant and the permanent, and we look at different symmetry groups. And I'll tell you what we know. The simplest symmetry group to consider is take the trivial group, which means you're imposing no symmetry restriction at all, and you're just looking at general circuits. The determinant we know you can do in polynomial time, and it is something like n to the omega, where omega is the complexity, n to the omega is the complexity of matrix multiplication. Omega is somewhere between 2 and 3, as far as we know. And you can turn that into a circuit for computing the determinant. For the permanent, the best known upper bound we have is something like n squared times 2 to the n. This is Reiser's formula, which I just showed you. And the best known lower bound we have is n squared. But remember, it's n rows and n columns. So really the matrix is of size n squared. This is just a trivial linear lower bound. It's completely trivial, but that's the best we know. We don't know of any non-trivial lower bound for general circuits for the permanent. You consider the sim-n symmetry, what I call sim-n symmetry or square symmetric, where you have a permutation pi and you apply it both to the rows and to the columns of your matrix. Then using Leverrier's method, we can compute the determinant with a circuit of size roughly n cubed for characteristic 0. Okay, we don't know it for other fields. We don't know how to adapt Leverrier's method, and we haven't found another method that works. But here, and this is what's interesting, for the permanent, we are able to prove unconditional exponential lower bound. Okay, and show that there is simply no sub-exponential size circuit which computes the permanent and which has symmetries. Now, note this matches this upper bound, and this upper bound is in fact a symmetric circuit, right, in this sense. So we have a sort of fairly tight match over here. Again, characteristic 0. We also consider what I call sim-n by sim-n, which is arbitrary permutations of the rows and the columns, which may be different permutation. This doesn't make sense for the determinant because the determinant is simply not invariant under this action. For the permanent, we can improve the lower bound a bit in a sense that we can prove the exponential lower bound not just in characteristic 0, but in all characteristics other than 2. Okay. So for any field of characteristic not 2, we can prove 2 to the omega n. Characteristic 2 is a very special case because in characteristic 2, the determinant and the permanent are the same polynomial because -1 equals 1. So, right? That's observation here. We then consider what I call the alt-n by alt-n action, even permutations for on both rows and columns. We can observe actually that our method over here applied over here and we get the same lower bound. But it turns out that with this action, we were able to prove a lower bound even for the determinant. We were able to show that there's no sub-exponential size circuit which computes the determinant with this group, rich group of symmetries. So in particular, not the full group of symmetries. So I told you we had a paper last summer at the ICAP conference. And in that paper, we really stated this result and this result. And people pointed out to us, first of all, that there's a gap between the two groups. And we observed that we could actually close that gap because we can get this one as a fairly easy consequence of this. Okay, and that really shows the difference between the determinant and the permanent. But people also said that this symmetry group, which is the simultaneous permutations of rows and columns, is not really the full symmetry group of the determinant. So what can you say about the full symmetry group of the determinant? And we essentially answer that question by showing this. That's saying if you go to a rich enough group of symmetries, you can't even do the determinant in some exponential size. Okay. So these are our results.
Yeah, sorry. And here you assume that the permutations of columns and rows are independent, right? So you don't consider
in this
all
case,
even. Yeah. So you don't
in this case, that's right. So
you don't consider all
even
permutations. So yeah, that's
an
right.
even permutation of the rows and an even permutation of the
independent. Okay, yeah, I see.
But separately, yes. Okay. So I mean, this includes in particular this, right? Because this is the same permutation of the rows and the oh no, I suppose it doesn't.
No, it doesn't, because it can be.
It doesn't. It doesn't. But the group D, which I call the full invariance group of the determinant, includes both of these, and obviously the lower bound from this obviously applies to that as well, right? Okay. So what I'm going to do, I want to give you some flavor of the methods involved in the proof, and I'm going to talk about this result in some detail, and then give you a hint of how that can be adapted to prove this one over here. Okay, how we adapt it to all 10. And I will also tell you how from this one, we get this one. But, well, also I'll tell you about the upper bound for the upper bound for the determinant I've already told you, Leverrier's method, that pretty much gives this. Okay, so I'm going to mainly concentrate on this. Okay. One observation. I stated the lower bounds in terms of the size of the circuit, but actually what we prove is a lower bound on what I call the orbit size, which is what we prove is that in any circuit which computes the permanent, for example, under this symmetry group, there is some gate whose orbit under the action of this permutation group has exponential size. So obviously that gives a lower bound on the size of the circuit, but in some sense it's a stronger statement. It says that there must be some gate with an exponential size orbit. Okay. So we obtained these results for arithmetic circuits by taking techniques we had previously developed for considering Boolean circuits. So Boolean circuits for deciding graph properties. So let me say a little bit about that. So a Boolean function, we say a Boolean function decides a graph property if it is a function from, if you will, a matrix of zeros and ones, n by n matrix of zeros and ones to 0, 1, and it is invariant under the action of sim_n. So the simultaneous permutation of the rows and columns. Why do I call this a graph property? Because basically, you can think of this as computing a decision problem on the adjacency matrix of a graph, in which it doesn't matter in which order you put the vertices of the graphs, right? That's we call this a graph property. Boolean circuits use gates of and or negation and threshold gates. What do I mean by threshold gates? This is a gate where you take some number of Boolean inputs and the output is 1 if the number of inputs, which are 1, is greater than some threshold t. Okay, so in fact, you can think of the OR gate as a threshold gate with t equals 1, the AND gate as a threshold gate with t equals the number of inputs. But this is the more general form. You can, of course, implement threshold gates with just AND, OR, and NOT, but not in a symmetry-preserving way. So you can't eliminate threshold gates while keeping symmetry without an exponential blowup. We had proved this before. Okay, but so our Boolean circuits will have AND, OR, NOT, and thresholds. So this is, I said, now if you have a polynomial P over a field K and variables X, where X are the indeterminate entries of some n by n matrix, and it is square symmetric, by which I mean sim_n symmetric, right? simultaneous permutations of rows and columns. Then we can think of it as computing some graph parameter taking values in K. So in other words, if you have a graph on n vertices, you're represented by its adjacency matrix, which we can think of as a function from x to 0, 1, which is the same as saying we fix some bijection from the vertices of the graph to 1 through n, and that means we have an adjacency matrix. Then the value of this polynomial is some parameter of the graph. And because we assume the polynomial is square symmetric, that means it doesn't depend on the choice of this bijection. You can choose a different bijection between the vertices and 1 through n, you'll still get the same value of the parameter, right? It's invariant under reordering the vertices of the graph. And so it really defines a graph parameter, a proper parameter of the underlying graph rather than of the matrix. If we start with a bipartite graph, so two sets of vertices A and B and an edge relation which relates A and B, we can represent it by a bijacency matrix. So the rows are indexed by A and the columns indexed by B. And then if the polynomial is matrix symmetric, invariant under arbitrary permutations of rows and columns, then it computes a graph parameter of this graph, right, given this matrix N. So, for example, you look at the permanent, and it's known that if I take a bipartite graph and take its biadjacency matrix, then the permanent is simply the number of perfect matchings in G. This is immediate to see because now all of these variables take values 0 or 1. When is this product equal to 1? I mean, this product is either 0 or 1, and it is a 1 precisely when sigma as a mapping from A to B, from the vertices to A to B, is a perfect matching, right? All the edges are present. And then you take the sum over all permutation sigma, which is all possible mappings from the rows to the columns. So you get the total number of perfect matchings. Take the same graph G, this bipartite graph, and consider its adjacency matrix. Its permanent is the square of the permanent of n. So the square of the number of perfect matchings. This is also not too hard to see, because what is the adjacency matrix of the graph G? Well, you'll have now both vertices from A and vertices from B in the rows and vertices from A and vertices from B in the columns. Because it's a bipartite graph, there are no edges inside A and no edges inside B, so these two matrices are all 0. This is the original biadjacency matrix, which tells you which vertices of A are adjacent to which vertices of B, and this will be its transpose. So what is the permanent of this matrix? Well, it'll be the sum over all mappings from AB to itself, where this product is 1. But for that product to be 1, basically, you can't use any of these zeros. So it'll have to consist of one perfect matching over here and another perfect matching over here. So the permanent is simply the number of pairs of perfect matchings, which of course is just the square of the total number of perfect matchings. Okay. So how do we do this? So we're going to get our lower bounds on arithmetic circuits by getting lower bounds on Boolean circuits. And for that, we simply have a translation. That is, if we have a gamma symmetric circuit computing some polynomial, there's now an arithmetic circuit, we can get a Boolean threshold circuit which decides for a 0, 1 matrix whether the value of this polynomial is in some fixed set B. So fix a set B of values, and I can construct a threshold circuit. The translation from C to C hat is not necessarily polynomial size, because in particular it depends upon this set B, and moreover, K is an arbitrary field. So, like if it may be a real field, then your set, you may specify real numbers up to arbitrary precision, and that can blow up the size. But the important thing we have is that the orbit size, the size of the maximum size of an orbit of a gate, is the same in C hat as in C. Okay. So I'm not going to give you a proof of this, but it is a fairly straightforward translation. And that means we can get our lower bounds for the size of the permanent by showing a lower bound for Boolean circuits, deciding whether the permanent, right, for we basically show that for any prime number C, deciding whether the number of perfect matchings of a bipartite graph is B modulo C cannot be done with sub-exponential size Boolean circuits. Okay. And that gives us the lower bound for the arithmetic circuit. Okay. So now how do we get these lower bounds for Boolean circuits? And there are a number of ingredients to the proof that I want to show you. I won't give you a full proof. I'm going to just give you, present you with some of the ingredients. One is obtained by considering what are known as the Weisfeiler-Lehmann equivalences on graphs. So the k-dimensional Weisfeiler-Lehmann equivalence relation, for every positive integer k, it's an equivalence relation on graphs, which is in some sense an approximation of the isomorphism relation. What do I mean by an approximation? Well, you have for every k an equivalence relation. As you increase the value of k, it's a finer equivalence relation. So two graphs which are equivalent at k plus 1 were also equivalent at k. So increasing the value of k refines the equivalence relation. If you go as far as the size of the graph, then it's the same as isomorphism, right? So it's a in the limit it approaches isomorphism with increasing values of k. I won't give you a full definition, but this has many different equivalent characterization. It comes from combinatorics, from logic. There's characterizations in terms of games, which I will show you. There's algebraic characterizations in terms of coherent algebras. It's characterized by linear optimizations. You know, it's a very natural family of equivalence relation which pops up in many places. In terms of logic, it's this equivalence relation means that they cannot be distinguished by any formula in counting logic with k plus 1 variables. Again, I'm not going to give you a definition. I mentioned this only because it motivates the name of this parameter I'm going to define next. If you have a class of graphs, I define the counting width of the class of graphs as the following function. For every n, you take the smallest value of k such that C is invariant under k. So our class of graphs, I'm assuming, is invariant under isomorphisms, which means for every n, there is some value of k, it's invariant under k, because if you take as k as big as n, this equivalence relation is an isomorphism. So in particular, we always have that nu C of n is less than or equal to n, right? That's always the case. More generally,
elements here mean vertices of graph, right? So so you consider here graphs.
Yes, vertices. We're counting the vertices. I should have said vertices. Yes. So I mean, so there are interesting properties for which this might be bounded by a constant. So for instance, the property that a graph contains a perfect matching has counting width bounded by a constant. This is a non-trivial result, but we proved this a few years ago. But now consider a numeric graph parameter. That means a function which assigns a value to any graph, a number in particular. And then we define the counting width of this function to be the smallest, to be the function which for every n gives you the smallest k, such that for n vertex graphs, if they're k equivalent, so it's invariant on the equivalence classes of k equivalence on n vertex graphs. Okay, so basically this is just a special case where mu is a 0,1 valued function, right? The class of the counting width of a class of graphs. Okay, and we know that any graph property which is decided by polynomial-size symmetric circuits has counting width bounded by a constant. I'll give you a proof sketch in a moment. This was something we proved in joint work with Matt Anderson a few years ago. 2017, this was the paper. And then we also know that if a graph property has linear counting width bounded below by some constant fraction of n, then any symmetric circuit for deciding it has exponential orbit size. Okay. With this, our lower bound for the permanent really boils down to proving that the counting width of the permanent as a graph parameter, or the counting width of the number of perfect matchings in bipartite graphs, is bounded below by n, right? Some constant fraction of n. Right? In contrast, as I said, the existence of a perfect matching has constant bounding width, but the number of perfect matchings, it turns out, has omega n counting width. Okay. I'm going to give you some idea of how we prove this. Again, as I said, the ingredients of the proof. What is the relationship between counting width, which is really this Weisfeiler-Lehmann dimension, and the orbit size of circuits? One ingredient is what we call the support theorem. So this is, if you have a permutation group gamma, subgroup of sim n, we say that a subset of n is a support of gamma if the pointwise stabilizer of S is included in gamma. In other words, gamma includes all permutations which fix the set, pointwise fix the set S. Okay. So that's what we call a support of the group gamma. And in a circuit, gamma symmetric circuit, we say that a set S is a support of a gate if the stabilizer of the gate has support S. In other words, once you fix all the elements S, then all permutations, all automorphisms of the circuit or in gamma also fix the gate G. Okay? That's what we call the support of a gate. For instance, the output gate, because it's a gamma symmetric circuit, is fixed by all permutations of gamma, right? So it has empty support. An input which is labeled with the variable xij has support ij. Any permutation which fixes I and j fixes this variable. It may permute other variables, right? If a gate has small support, it has a large stabilizer group because all permutations of elements outside the support fix the gate. And because it has a large stabilizer group, it has a small orbit. Our support theorem is really a converse for this. If a gate has a small orbit, then it in fact has a small support, right? So basically it says if the orbit size is at most n to the k, n choose k, sorry, then there's a support of size less than k. Which means in some sense, the only way you can have small orbits is if G is really determined by a small number of elements, and permuting everything outside will leave G fixed. Okay, so basically the stabilizer of G has small index in sim n, then it contains a large symmetric group, right? This is specifically for sim n symmetric, I should say. Okay, so note, this is not simply a fact about all groups, right? There are groups, subgroups of sim n which have small index, but don't contain a large symmetric group. And the obvious example is the alternating group, right? It has index 2 in sim n, but its smallest support has size n minus 1 because there isn't any subset of n such that all permutations, any large subset of n such that all permutations of it are contained in the alternating group. You actually have to fix n minus 1 elements to get that all permutations of the remaining elements are in the alternating group. As long as you have 2 elements outside, the swap is not in the alternating group. Okay. But it turns out that the alternating group is really the only obstacle, right? It's the only thing of small index which doesn't contain large symmetric groups, in the sense that this is a classic theorem. You can find it in a textbook on permutation groups, that if you have a subgroup of sim n with index smaller than n choose k, then you can find a small set such that alt S is in gamma. What is alt S? This is all even permutations of elements outside S, all even permutations which fix the points in S itself. So this says basically that any subgroup of sim n which has small index contains within it a large alternating group. And then we get our support theorem from the circuit by showing by induction on the structure of the circuit that when the stabilizer group of a gate contains a large alternating group, it necessarily contains a large symmetric group. Okay, right. That's this support theorem is one ingredient of our proof connecting the Weisweiler-Leman dimension to circuit size. The second ingredient is a characterization of this Weisweiler-Leman equivalence in terms of what are called bijection games. This is due to Hella and was proved back in 96. What is a bijection game? It's a game played on a pair of graphs G and H by two players we call spoiler and duplicator. And they have a number of pebbles, A1 to AK, which will be placed on vertices of G, and B1 through BK, which will be placed on vertices of H. And think of this game as spoiler is trying to prove that these two graphs are different, and duplicator is trying to pretend that the two graphs are really the same. And here are the rules of the game. Spoiler chooses a pair of pebbles, AI and BI. These might be pebbles already in play, or they may be not yet in play, but the total number is limited to K. Duplicator has to give a bijection between the vertices of G and the vertices of H, with the property that for AJ and BJ, which are already on vertices of G, this bijection should take the vertex under AJ to the vertex which is labeled by BJ. Okay, so I'll illustrate this with a picture in a point. Then spoiler chooses some vertex in G and places this AI on that vertex and BI on its image under the bijection. If the partial map fails to be a partial isomorphism, duplicator has lost the game. Otherwise, the game can continue. And if duplicator has a strategy to play forever, this characterizes this equivalence relation, the K-1 Weisweiler-Leman equivalence between G and H. For our purposes, you can take this as a definition of this equivalence relation. Let's illustrate this with a picture. At some point in the game, we have the graphs G and H. A1, A2, and A3 have been selected. There's a pebble on this vertex, and this vertex, and B1, B2, and B3. And the map which takes A1 to B1, A2 to B2, and A3 to B3 is an isomorphism on the induced subgraph. So this is okay for duplicator. Spoiler says we're now going to place A4, and duplicator has to give a bijection H on the whole graphs. And then spoiler chooses some element, A4, and its image HA4. And now there's a pebble on A4 and HA4, and this local isomorphism condition has to be preserved. So basically, duplicator's bijection H would have had to satisfy the condition that it preserves all adjacencies to A1, A2, A3, and B1, B2, B3. And then in such a way that the game can carry on for another move and another move and so on. But the point is that you can only have K vertices pebbled at a time. After K moves have been played, spoiler has to remove some pebble to carry on the game. Okay, that's the bijection game. Now, with the bijection game and the support game, we have our tools for proving lower bounds for symmetric circuit. And the key is the following connection. If you have a symmetric circuit, and symmetric for now means sim and symmetric, let's say. Okay. And the input is an n-vertex graph. In the sense it's the adjacency matrix of an n-vertex graph. Because C is sim and symmetric, it doesn't matter in what order you put the adjacency matrix. If every gate in C has a support of size at most K, and G and H cannot be distinguished in 2K Weisfeiler-Lehmann equivalence, then C cannot distinguish these two graphs. If it accepts one, then it must accept the other. Okay. How do we do this? We basically prove that if the circuit can distinguish, if it gives different answers on G and H, then the circuit describes a winning strategy for spoiler in the 2K pebble game played on these graphs. And the idea is quite simple. You basically, spoiler fixes some bijection from the vertices of G to the inputs of the circuit. I mean, that's just saying you fix some adjacency matrix representing G. And in the bijection game, Duplicator maintains a pointer to a gate in the circuit and the current position in the game. Now, U and V are tuples of selected positions. So alpha of the currently pebbled positions is a support of the current gate. So it includes the full support of the gate. And whatever bijection you choose to map the vertices of H to N, as long as it maps U to V, B inverse alpha maps U to V, then this gate distinguishes this gate. This means they evaluate this gate with this inputs and evaluate the gate with this input. They should give you different values. Okay. So really in this, here's the picture. We have the circuit. Alpha is some way of mapping the graph G to the inputs. Beta is a way of mapping the graph H to the inputs. And here is some gate such that when you apply alpha G to the inputs, this gate gives you a value 1, let's say. And when you apply beta H, the gate gives you a value 0. Okay. Initially, because we're assuming the circuit distinguishes them, for any alpha and beta, this is true at the output. But now you will follow this through the duplicator strategy will essentially, follow a path to the inputs, showing a difference between G and H. And duplicator will change the bijection between G and H at various points, and that corresponds to changing beta, right? Whenever duplicator changes the bijection, you compose that with alpha to get a different beta over here. But as long as the currently pebbled positions are not changed, this is okay for spoiler. Okay, I realize this is very sketchy. I have a bit more detail on the slide, but I don't expect you to read it. So as I said, on the output gate, by assumption, they have different values for any beta. And at the induction step, while keeping the pebbles on the support of G, or rather the alpha inverse of the support of G, spoiler moves the other K pebbles onto the support of a child of G. At each move, duplicator plays some bijection, and spoiler has to then choose, spoiler can still choose an H, which distinguishes alpha G from alpha gamma inverse H. Okay, I've got a little picture. So basically, in K moves, spoiler can move. This gate distinguishes alpha beta to some child of that, some predecessor of that, which still distinguishes alpha beta in the currently pebbled position. And eventually you will reach an input, and which will be true of G and false in H, which means that the current pebbled position is not a partial isomorphism, so spoiler has won the game. Okay, so as long as there's a circuit with small supports which distinguishes G and H, we can construct a winning strategy for spoiler. Contrapositively, if duplicator has a winning strategy on G and H, then no circuit with small supports can distinguish them. Okay. So we get lower bounds for the size of symmetric circuits for the permanent by simply showing that for any odd prime C, the counting width of the number of perfect matchings in a bipartite graph is omega n. So basically we can, which means that we can construct, writing mu G for the number of perfect matchings, we can construct for each K a pair of bipartite graphs with a number of vertices linear in K, which are K equivalent, but the number of perfect matchings in G is different from the number of perfect matchings in H. And in fact, we construct them so the difference is a power of 2, which means they're not equivalent modulo C for any odd prime C, right? Because the difference is a power of 2. And that establishes, as I said, our lower bound for the permanent, for the matrix symmetric case, for all characteristics other than 2. The construction is based on Seyfert-Immermann graphs. I'm not sure I'm going to keeping an eye on the time. I will skip the details of the graph construction because I'm not sure it is that instructive. If you've seen the Seyfert-Immermann graphs before, it's a similar idea. The main technical difficulty is we adapt the construction a little bit. So the Seyfert-Immermann construction gives a way of constructing pairs of graphs which are indistinguishable with k-dimensional Weisweiler-Leman. We have to adapt the construction to be able to show that the number of perfect matchings is different in the graphs. Okay, and the main adaptation, is including this balanced vertex. We show it doesn't change the other properties of the graph. Okay, let me kind of skip over this bit of the construction. The key observation we get is that as I said, the number of perfect matchings is a power of 2, and from that we conclude that there's no family of matrix symmetric arithmetic circuits of sub-exponential size which computes the permanent as long as the characteristic of the field is other than 2. So that was aimed at proving this result. I told you this one is a sort of fairly easy consequence. Once you realize what I said, that the permanent of the adjacency matrix of a graph is simply the square of the permanent of the bi-adjacency matrix. So if you have a graph, our construction gives a pair of bipartite graphs which have a different number of perfect matchings, and their difference is a power of 2. If you actually take the adjacency matrix rather than the bi-adjacency matrix of these graphs, they have this Simon symmetry. And obviously, these also have different numbers of, these have different permanents because the permanent is simply the square of the number of perfect matchings, and the number of perfect matchings is different. Now, we don't know, and our construction doesn't tell us that the difference of the squares is a power of 2, right? So that's why we can only claim this for characteristic 0. We know that the difference of squares is different. So, in any field of characteristic 0, it will be different. But knowing that the difference of the numbers of perfect matchings is a power of 2 doesn't tell us that for the difference of the squares. Okay, so now let me tell you a little bit about our most recent work, which is looking at this. So really, we were using games on graphs. We're establishing lower bounds for polynomials on matrices. But we're really using games on graphs, and this was quite natural because this symmetry group is really the symmetry group of the adjacency matrix of a graph. And this is the symmetry group of the bi-adjacency matrix of a bipartite graph. Okay, so just by playing games on bipartite graphs, we're able to establish lower bounds for both of these symmetry groups. This one, it's very hard to think of as the natural symmetries of a graph. So what we did was we changed our notion of equivalence, and we changed the notion of game accordingly to establish this. And I just want to give you the idea involved here. So we're trying to prove a lower bound on the determinant under what I call the even symmetrics action. And we adapt the proof from the sim-n by sim-n symmetric lower bound for the permanent in a number of ways. First of all, we adapt the support theorem to give us for subgroups of alt n rather than sim-n. But this is actually the easy bit because it's actually easier for alt n than it was for sim-n. We define a generalized version of the bijection game, which works for gamma symmetric circuits for general gamma rather than just sim-n symmetric circuits. And then actually the hardest work is constructing these matrices with different determinants. And we do get them again as bi-adjacency matrices of bipartite graphs on which we are to play these spoiler duplicator games, but these generalized games. So the support theorem, as I said, this bit is relatively easy. I've just rewritten it, putting all 10 here instead of Sim-n. This is already known. Again, you can find it in standard permutation group textbook, like by Dixon and Mortimer. And once we have this, we don't even have to do our argument by induction on the circuit because we already have the alternating group we want over here, right? So the support theorem just follows from a more general version of the Jardin-Liebig theorem. The bijection game, here's the variation now. We fix a group gamma, which we think of as a subgroup of the permutation group on the vertices of H. Again, we have a pair of graphs G and H, and we fix an initial bijection H. The game proceeds again. Spoiler chooses a pair of pebbles. Now, duplicator cannot play an arbitrary bijection between VG and VH. Duplicator is only allowed to play certain bijections, namely those which you can get by composing this initial bijection with a permutation from gamma. Okay, so note in particular, if gamma is the full symmetry group, then this is any bijection. So that we're back in the original bijection game. What we're doing here now is restricting duplicator to some subset of bijections given by gamma and this initial bijection. And the rest of the game proceeds as before. Spoiler chooses a pair of pebbles. Winning conditions are same as before. So the game carries on, except the whole point is that duplicator is not allowed to play arbitrary bijections, but those restricted from some, if you will, a sort of affine subspace. Note, in the ordinary bijection game, if there is in fact an isomorphism between G and H, that isomorphism just gives duplicator a winning strategy. Always play that isomorphism as a bijection. This is no longer true here because there might be an isomorphism, but that isomorphism simply is not available to duplicator in this set of bijections. Okay. So as a picture, it's now non-trivial to play this game even on two copies of the same graph. So these are the same graph, they're isomorphic, but the initial bijection H is not an isomorphism. So here I'm picturing a bipartite graph where H is the bijection, which is the identity everywhere except X and Y, and we have mapped X to Y and Y to X. Okay? So think of it this way. If we have the bi-adjacency matrix of this graph, this is the same graph, but we're considering the matrix where we have swapped two columns. So in particular, if this bi-adjacency matrix had non-zero determinant, the determinant here is of opposite sign, so this cannot be an isomorphism, right? And we now, let's say, restrict duplicator to playing bijections which are composed of an even permutation at the bottom and an even permutation at the top, then you can never hit an isomorphism because, you start off with determinants of opposite signs, you apply an even permutation to the rows and an even permutation to the columns, you still have determinants of opposite signs. So it is, even though the graphs are isomorphic, it is non-trivial for duplicator to have a winning strategy. And what we show is basically that this gamma restricted bijection game gives you lower bounds on gamma symmetric circuits in the same way as the bijection game gave us lower bounds for Sim-n symmetric circuits. Okay. And then we have a CFI-like graph construction. You apply it to a graph which yields a bipartite graph whose bi-adjacency matrix has non-zero determinant. And then we show basically a winning strategy for duplicator in this all 10 by all 10 restricted game, which is on two copies of the same graph, but with an initial bijection which swaps two elements on one side of the bipartite graph. And it turns out we can show this as long as the initial graph G satisfies a number of properties. It has to be itself a three regular bipartite graph with large tree width and an odd number of perfect matchings. And in some sense, the kind of hard work in this whole proof ultimately was giving a construction of a graph which satisfies these properties. But this is, when I say a graph, obviously I mean one for each n. And really, when I say large tree width, I mean omega n, right? Where n is the number of vertices. So that's what gives us the linear lower bound on Weisweiler-Lehmann dimension, and hence the exponential lower bound on the number of on the size of the circuit. Okay, I mean, obviously, in time available, this is not a full proof, but I hope I've given you a flavor of the kinds of things that went into the proof. And I think I'll close with this summary of the results again, right? As I said, this we have a paper on the archive, which really, well, it's an updated version of the ICAP paper, and it really contains these results, this one and this one. This lower bounds on the determinant is new work, not yet fully written up. But I'll stop here and happily take any questions.
Thank you very much. Does anyone have questions? Yeah, so I have one. So here on this in this table, the lower bound in the first column, I mean omega of n squared. So is it only a trivial or lower bound or some constants in front of n squared, non-trivial constants?
No, it's just the trivial lower bound. I mean, I'm not aware of any non-trivial lower bound specifically for the permanent. I mean, there are some lower bounds more than linear known for some polynomials, but not for the permanent that I know of. Okay, the only lower bounds for the permanent I know are in restricted classes of circuits rather than for general circuits. Okay.
But for determinant, there should be the same lower bound, right? By the same reason, or not?
Yes, sure.
Okay,
yeah.
And
you can put omega n squared here.
Yes, that's right. And here, yeah. So in the second case for this symmetric group, there is no better lower bound than just trivial n squared.
Here.
Yeah.
No, we didn't really. Okay, no, we haven't really looked at this. That's an interesting question, because I wondered about this, right? Because here I put n to the omega, which is the complexity of matrix multiplication.
Yes,
and basically, right. You can reduce determinant to matrix multiplication. But I don't know how to do matrix multiplication symmetrically better than n cubed. And so possibly you can actually prove an n cubed lower bound even for matrix multiplication under a suitable symmetry restriction. And we looked a little bit at that, but I don't know how to do this. Roughly speaking, the method we have, which is based on these Weisweiler-Lehmann things, they give you exponential lower bounds. And you can imagine proving a lower bound like n cubed by giving a reduction from, let's say, permanent to determinant, which is of something like order 2 to the n over 3, which means if you could do this in better than n cubed, you would have something better than 2 to the n over here. except that doesn't work because this omega hides some big constants, right? And this 1/3 is completely swamped by that constant. So I don't know how to do better. I mean, and I don't know, other than this Weisweiler-Lehmann method, I don't know of any other method for proving lower bounds for the symmetric circuits. So yeah, this is why I don't really know how to prove a lower bound here.
Okay, see. Thank you very much. And one more question. On the previous slide, when you construct your graphs, I'm not very familiar with this connection with all these things. So can you please repeat why you need large tree widths?
I see. So so here is, well, actually, let me go back. I skipped over the CFI construction, and it's worth maybe talking a little bit about this. So you start with a 3 regular graph G, right? And you look at a vertex with 3 edges, which we'll call FGH. Every vertex in G, you replace it by this gadget. Okay? What is this gadget? You replace the vertex by these, you replace every edge by 2 new vertices. I'll call it F0, F1, G0, G1, H0, H1. And now you replace the central vertex V by these 4, plus this additional 1, which we can ignore for now, these 4. And they're labeled, you see, by all subsets of FGH of even size, the empty set and the 3 2-element sets. And I connect them, I connect VFG to F1 and G1 and to H0, right? Because H is not in the set FG, so it goes to 0, and it goes to F1 and G1 because F and G are in the set. The empty set connects to F0, G0, and H0, and so on. Okay, this gives me this graph XG. I get a different graph X tilde G by in exactly one vertex. Instead of the even size subsets, I take the odd size subsets. Okay, and then if the original graph has large tree width, I can show that these two things are K equivalent. And this is basically, you play the bijection game on these two graphs, which look very similar. Okay. And duplicator strategy is to hide the difference somewhere which is not in a currently pebbled position. And essentially, by swapping elements like this, you can interchange F0 and F1, and this gadget starts to look exactly like this gadget, right? If you just exchange any one of the 3 pairs. And which means that basically you have hidden the difference in the next gadget. And then you can swap a pair and hide the difference in the next gadget. And the thing is, as long as the underlying graph has large tree width, you can move this difference anywhere in the graph. And with K pebbles, spoiler cannot block it. Okay. So basically, you use the tree width of the underlying graph to lift to this K pebble bijection game on these graphs XG and X tilde G. Okay. Does that make sense?
Yeah, it makes sense. Thanks.
Okay.
Okay, is this condition with tree widths necessary or not?
So I mentioned here the original Cipher-Immermann proof relied on the existence of balanced separators.
Mm-hmm.
And then we characterized it in terms of tree width. Now, we didn't know, so we don't have a converse, but I suspect, I mean, so tree width is already a strengthening of the original Cipher-Immermann, but we don't have a proof that if G has small tree width, then you can distinguish these always. Yeah, we don't have that direction.
Mm. Okay, thank you very much. Are there any other questions?
Yes. Hi.
Hi.
Thanks for your talk, first of all. I was wondering, you mentioned that there's an issue with characteristic 0 or non-zero for the determinant.
Let me see. So, well, our two upper and lower bounds are only proved in characteristic 0. So, for example, Leverrier's method, which computes the determinant based on the traces, we don't know how to do this in positive characteristic. That's basically because it involves division by arbitrarily large constants up to the size of the graph, or up to the size of the matrix. And yeah, so we don't know how to do that.
So I was wondering because I was wondering because there's this algorithm by Meena Mahajan and others, which is purely combinatorial and computes the determinant by summing over these so-called Claus sequences, which are like relaxed cycle covers. So I'm assuming that something goes wrong when you want to do this symmetrically then, or?
That's right. We looked at it and we couldn't work out. I mean, it basically does rely on processing the vertices in a certain order. And we looked at it and we couldn't make that work. So.
Okay. And then I have a more general question, maybe. Is there some sort of toolkit for investigating the counting width of graph parameters? So you mentioned this approach of taking Seifert-Immermann graphs and having some property that differs on a CFI pair, and then showing that, like the number of perfect matchings. But is there maybe some other way that is maybe going more directly into the spoiler duplicator strategy, or something that sidesteps this completely, like some general statements that allow you to prove lower bounds on graph parameters?
Well, I mean, so you don't have to do a CFI-like construction every time, because you can also do reductions. So if you have sort of symmetry-preserving reductions, like reductions defined in first-order logic, they will allow you to transfer statements about counting width from one class to another. So, you can so there are other sweeping statements, like for constraint satisfaction problems. Any constraint satisfaction problem which is not of bounded width has a linear lower bound on its counting width. Okay. And this is proved entirely by a sort of general mechanism of reductions from a CFI-like construction to begin with. So I think the one general tool is that of symmetric reductions, if you will.
But then you would say that the starting point is usually some CFI-like thing.
Yeah.
And is there some way of composing strategies maybe for a bijection game? Because in the standard Ehrenfeucht Fresse games, there are some ways of composing strategies, right?
So sort of, well, certainly sort of it'll compose with, say, disjoint unions of graphs, but maybe that's not so interesting. Yes, I mean, it'll possibly compose with some kind of graph product as well. I think that would work. So, I mean, I mentioned all these different characterizations of the K-Weiss-Faraday-Riemann equivalence. I mean, there's another recent one I could have mentioned is a sort of category theoretic one. You can view this as isomorphism in the Kleisli category of a certain comonad on graphs. And that gives a compositional structure in a sense, because I mean, that's what categories allow you to do. But I'm not sure that that's a very usable tool. It's, yeah.
Thank you.
Other questions?
If I may, my question is, are there any results about Boolean circuit complexity of Boolean functions, except for results that appear in your argument? for example, a majority or any threshold function, they're perfectly symmetric. Do we have a polynomial time symmetric circuit for the majority function?
Sorry, I kind of, yes, I implied this. Let me go back. So where did I introduce? Oh, sorry, I'm going back. When I mentioned Boolean circuits, was it further back? Sorry, this is further back than I thought. Here we go. I mentioned we use and, or, and not. And I said you cannot eliminate threshold gates while keeping symmetry, which basically means any symmetric implementation of threshold gates by and or not must be exponential.
It can be proven that it must be exponential.
Yes, exactly. Okay. And this is same is true for majority. In here, if I replace threshold by majority, it makes no difference. So I can use majority instead of threshold. But that also implies that any implementation of majority using and or not, which is symmetric, must be exponential.
Thank you.
Okay.
Any other questions?
What about estimations of depth?
Sorry, estimations of depth. You
For
mean
example,
of these
proof
of the depth of the circuit?
Yeah. Yes.
So we're not putting any bound on the depth. Okay, so the lower bound applies to circuits of any depth whatsoever. I suppose, I mean, the right. I mean, the thing we're bounding below is, as I said, really the orbit size. And so circuits of any depth, as long as they have small orbit size, cannot compute the permanent. For the upper bound, for the determinant, the n cubed upper bound, I don't think you get a depth much better than n cubed. It's not a sort of parallel circuit because actually, do I know this? Yes. Okay. I think it's a linear depth there. But yeah, that's all I know.
Okay. Thanks.
Any other questions?
Thank you for inspiring talk. I wonder, is there any hope to develop similar approach for immanence?
Well, I mean, obviously the permanent and the determinant are both special cases of immanence. But that's a very good question. I don't know of okay. I'm trying to think what I mean. I haven't thought about this, and I'm trying to think if there's anything general we can say. Obviously, I mean, if a lower bound for the permanent is in some sense a lower bound for immanence in general, because permanent is a specific immanent. But I'm not sure if I can say anything more. But yes.
So I happen to be working on this right now.
Oh, yes. Okay, can you tell us something?
Yeah, so I guess there are two ways of doing this. Like the direct way would be to somehow figure out the counting width of an immanent.
Right.
And there somehow it would interpolate between determinants which have very low counting width and permanents which have high. And the other way would be somehow to actually use reductions, because so I devised a hardness proof for immanence recently, and there all the reductions actually come from counting perfect matchings. So if you can somehow encapsulate this problem of counting perfect matchings in an immanent while preserving symmetry in the reduction, then you probably can transfer the lower bound.
Okay, sounds interesting. I would like to see this when you have something to share. Yes.
Yeah, would be very
Yeah,
happy to share
certainly.
that.
Looks very interesting, this idea.
Does anyone have questions? Thank you very much for the very nice talk, and it was very interesting. Thanks everyone for joining. I think that's all for today. See everyone next Thursday. Goodbye, Anuj. Goodbye, everyone. Bye-bye.
Okay.
Thanks.
Thank you. Thank you very much for having me. It's
Thanks.
very enjoyable.